Fraunhofer diffraction at circular aperture. In earlier lectures, we studied Fraunhofer diffraction at single slit, then we studied Fraunhofer diffraction at double slit, and in this lecture, we will study Fraunhofer diffraction at circular aperture. As you are aware that to distinguish two nearby objects, the lenses are used. For example, in case of telescope or the microscope, to see the nearby objects or to magnify the objects, we are using the lenses. Now there is a problem of using the lenses. The first problem is there is a lens aberration. Lens aberration is nothing but inability of light rays to focus at a single point. Since they cannot focus at a single point, we cannot distinguish nearby objects because there would be the spread of the light. And if there is a spread of the light, we cannot distinguish the objects which are very close to each other. In addition to lens aberration, there is a diffraction also. You know, this diffraction also spreads the light. So this diffraction and the lens aberration limit ability to distinguish nearby images or objects. And most of the optical instruments, there are circular lenses used to magnify the objects. So why to study then Fraunhofer diffraction at circular aperture? It is important to study Fraunhofer diffraction at circular aperture because this optical device called the lens can be regarded as circular aperture. Even our eye is also a lens or which can be regarded as circular aperture. So there would be diffraction at this circular aperture, and that's why it is important to study diffraction at circular aperture. So let us first see the diagram. So this is the diagram of the Fraunhofer diffraction at circular aperture. In this case, this AB. Now AB is not a single slit. It is single circular aperture. I cannot show here circular, so I have shown like a slit. So this AB is a circular aperture of diameter D. In other diagram over here, you can say that this is the circular aperture and diameter of that circular aperture is equals to small d. This is equals to small d. So we have a circular aperture in this case in this two-dimensional diagram. This AB is the circular aperture whose diameter is d, and this W is the plane wavefront whose wavelength is lambda. Then when this wavefront incident on this circular aperture, then as per the Huygens theory, every point in the circle in, into this circular aperture acts as a secondary source and emit secondary waves in all directions. So in this case, in this circular aperture, every point here acts as a secondary source and emit secondary waves in all directions. Now in the two-dimensional diagram, I am going to show the secondary waves which are diffracted and at an angle 0 with normal to the plane of the circular aperture. That secondary waves are focused at point P0. Okay, they are focused at this point and we are calling this point as a P naught. But at P naught, we will get a circle, a bright circle. So cone of light will be formed because of the diffraction from the circular aperture. The cone of the light will reach at point P naught. So let me show here the cone of the light over here. This is our small circular aperture. So the light which is going in this way, which is reaching at this point P naught, and here at point P naught, will get a circle, a bright point which has some diameter, and this bright point is formed because the cone of the light is reaching at this point. So at point P naught, we will get a bright circle. Then those diffracted rays from the circular aperture, which makes an angle theta. They will, let's say, they will reach at point P1. So these are the rays which are making an angle theta, and these secondary waves are reaching at point over here. Let's call it point P1. So we are going to consider only point P0 and P1, and let's assume that the distance between these 2 points is x. Now since this is the circular aperture, the diffraction takes place at the circular aperture. So on the screen, instead of seeing the dark and bright fringes, you will see dark and bright rings. On the screen, you will see dark and bright rings. And this dark and bright rings pattern is called Aries pattern. Aries is the name of the scientist who gave a good explanation for this diffraction. So that pattern is called the Aries pattern. So on the screen, as you see here in this diagram over here, you will see alternate dark and bright rings whose intensity fades away as we go away from the center. So at point P naught, what we will get is a, a bright spot like this, a big bright spot which has some diameter or the radius, and this the big bright spot which is formed, that bright spot is called the Aries disk. So at the center over here, as you can see here in this diagram, at the point P naught over here, you will get at this point is P naught, where you get the Aries disk. And surrounding to this Aries disk, we get dark and bright fringes. So who formed these rings? Why the rings are formed? The rings are formed because secondary waves traveling in the direction in the form of a cone like this. These secondary waves are traveling in the direction in the form of a cone, and because of that, the rings are seen on the screen. Okay, the rings are seen on the screen because now that there is a diffraction takes place from the circular rings. So on the screen, you will get alternate dark and bright rings. Let us say that at point P1, who is at a distance x from the point P0, we get some ring, dark or bright. And then this x is nothing but radius of the first ring whose center is at P naught. Okay, at this distance x, we will get the ring. And the center of that ring is at point P naught. So you can say over here, this is the point P naught and this is the distance x. So x is nothing but radius of the first ring whose center is at point P naught. In this case, this is the point P naught. So we get a radius, we get a circle, we get a ring whose radius is x. It is either dark ring or bright ring. That depends on the path difference between the waves which are starting from the point A and B. Okay. What would be the path difference between the waves which are starting from point A and B? Those waves which are starting from point A and B, which are reaching at point P1, and then at point P1, you will get ring, dark or bright, that depends on the path difference. And the path difference is nothing but this length. By drawing the perpendicular, this is the path difference. As you know that the diameter of the circle aperture is d. So this distance is d, this angle is theta. So d sine theta is the path difference. This length is nothing but d sine theta. So the path difference is d sine theta. D sine theta is path difference. And when this d sine theta is equals to n lambda, what we'll get? When d sine theta is equals to n lambda, as per the diffraction condition, we will get the minima. This is not the interference, this is the diffraction. So when d sine theta is equals to n lambda, as we studied earlier that when a sine theta is equals to plus minus m lambda, we get minima. So in this case, instead of d, it is instead of a, there is a t. So when d sine theta is equals to n lambda, we get the minima, and when this d sine theta is equals to 2n minus 1 or plus 1 upon lambda by 2, we get maxima. So when d sine theta equals to n lambda, we will get the dark ring, and when d sine theta equals to odd multiple of lambda by 2, we will get bright ring. Now let's assume that if this lens is very close to circular aperture, okay, when this lens is very close to circular aperture, then the light is focused at point P1. Okay, light is focused at this point. Lens is very close to the circular aperture. If lens is very close to the circular aperture and light is focused at point P1, then what would be this length? OP1. How much would be the length OP1? How much would be this length if lens is very close to circular aperture? Obviously, when we are focusing the light using the lens, and when the light is focused, then the distance between the lens and the focused point is equals to the focal length. So focused point is P1, lens is over here, so this distance would be then F. distance from point O to P1 would be f, the focal length of the lens. Let's write that if lens is very close aperture, then sine theta is equals to, now see the diagram, let's see the diagram. In this theta equals to the length x, this is x. So length, this x divided by f. If the lens is very close to the aperture, then sine theta is equals to x upon f. This is our equation 1. In this case, f is focal length of lens. We already have the condition for the first minima. For first minima, just now we wrote that when d sine theta is equals to lambda, because n equals to 1 for the first minima. So d sine theta is equals to lambda is the condition for the first minima. From this equation we can write sine theta is equals to lambda upon d. What is d? D is the diameter of that circular aperture. And let us assume that this is equation 2. Then from equation 1 and 2, from equation 1 and equation 2, we can compare it. We get x upon f is equals to lambda upon d, or x is equals to f into lambda upon d. And what is x? This x is nothing but radius of Aries rings. It is a radius of Aries ring. However, this is what we get from these calculations. But this Aries shows that the scientist Aries showed that actual value is not x equals to f lambda upon d. Actual value is equals to, there is a correction which is 1.22 times f lambda upon d. So radius of the Aries ring would be equals to 1.22 times f lambda upon d.